average treatment effect can be computed by solving two regression problems. You have double expectation, inner expectation is 1, and then you have outer expectation with respect to marginal distribution of x, and this number is something you can evaluate from there. Now, that's the AT, average treatment effect, and it is identifiable, but there are practical problems. So, this estimate might be biased if the overlap between two treatments, overlap of covariate distribution between the two treatments is not great, is not strong. Another thing that can happen is that you can have a high-dimensional confounder that may be hard to condition on, practically speaking. So these expressions might be difficult to evaluate. Okay. So then one idea comes to mind, especially when you want to use neural networks. Can we use neural networks to learn a representation for x? Okay. And maybe that representation will be good enough for me to do adjustment, or maybe I won't even need to do adjustment. Okay, we'll see what that means. So we will use x to get a representation of x that we will use later on. That's the takeaway. Okay, so this is the function modeling perspective, just to remind you, we are operating in. And here's an example I constructed to showcase the problem. Let's say you have two treatments, t equals 0, t equals 1, binary, and you have a continuous covariate that's one-dimensional. It takes all these values, and the shade of color here represents the outcome y. So this is your observational data set. Now, what do you see here? You see an overlap problem. So you don't have the values here. When t equals 1, you don't know what happens to y for these values of x. And when t equals 0, you don't know what happens to y for these values of x. Okay, so that's called the overlap problem. Now, if you naively do adjustment, or this least square regression, right, if you have linearity, then you will see that if you intervene, then the gap will be very large. So if you look at, let's say, simply average here versus average here, the gap is huge. So you're going to think that intervening on t equals 1 versus 0 has a very large effect on y. Right? And this you can see from the naive approach. You estimate the coefficient or causal effect, or the coefficient to be 6, whereas in reality it's actually just 2. Okay? How t is affecting, according to this graph, how t is affecting y, the coefficient here for a linear model is just 2, but you measure it to be 6 because of this bias, so the overlap issue. Okay, so if you could magically access, right, let's say you could magically access to these counterfactual samples. So for each circle here, let's say you could get the corresponding triangle for do the other treatment. So for these points, I'll get these triangles, and for these points, I'll get these triangles. If I could do that, then I'll see that each point only changes the shade of color just a little bit, right? And when you look at the average change, you will measure it correctly. So this is the missing data perspective of causal inference problem. Fundamental problem of causal inference is a missing data problem. You will never observe two treatments at the same time for the same person, or the same covariate in this case, when you have overlap problems. Okay. So what they want to do here is the following. So we want to get to this function h that takes two values, x and t. So it takes the covariate and it takes the treatment value, and it gives you both the factual value and the counterfactual value. So from here, I want to get to here. I want to be able to fill in these values using some function h that I learned from my data. Right? So the question is that even possible, or maybe under which assumptions would that be possible? So the takeaway is, if we can model the function h, we can use it to obtain counterfactual pairs. I just need to flip t to 1 minus t for the same x, and that's a counterfactual sample, and you can use it to estimate average treatment effect, or even individual treatment effect, which is condition on x. But you have missing data problems. Right? So we need to fill in the missing data, missing values smartly. So what they propose to do in this paper is they would like to distill the confounder X in a way so that it has balanced distribution across two treatments, t equals 0, t equals 1. If the distilled version of the representation has the same distribution, then maybe it's as if you actually conducted an experiment, randomized controlled trial, and used the same distribution. And if you do that, it's going to be easier to learn this function h on this balanced representation. And here the solution will be to use deep learning to obtain a representation, keeping these objective functions in mind. But the question here is that why would this even work? Or when should it work? So at this point, I'm going to slightly diverge from the paper to discuss something. So let's say I'm interested in this general fact. I have this causal graph, x causes t, x causes y, t causes y, and I want to do adjustment with a representation of x. Again, maybe x is an image, very high dimensional, I cannot condition on every possible image, so I need to find another way. When can you use a representation? So let's say w is the representation. Now, you will notice I will obtain w after processing x. So x goes into a neural network and comes out w. So if you append this w into the causal graph, it must come as a child of x. Because if you change x, it affects w, but not the other way around. Okay? So this is the true causal graph that you are dealing with. Okay, so first, that's the first thing we need to understand. And if you look at this causal graph, you will see that w actually is not a valid adjustment set. If you condition on w, t, let's say the civic here, t and yt are not independent given w anymore. Because conditioning on a descendant of x doesn't actually block it. But maybe there are some assumptions under which I can use such a representation for adjustment. So that's what we are going to try to discover. So what was the paper after? The paper is after a representation w that is balanced. And here balanced means if you condition on treatment equals 0 versus treatment equals 1, you get the same distribution for w. That is literally independence. So it assumes w and t are independent. And you also would like w to be informative, because what I can do is I can always map x to w equals 1 or w equals 5. I can map it to a constant. But clearly you cannot control with a constant. You need to have this edge intact. If it's a constant, there's no edge. So let's call this informativeness. And by that we will mean that if you condition on w, then y and x become independent. Okay? So that means w contains all the information that x has about y. And again, that's not obvious from the graph. Actually, none of these are obvious from the graph. None of these are entailed from the graph. But you might be able to still entail it, because not every distribution has to be faithful for causal discovery folks out there. Okay, so this informativeness removes trivial representations such as a constant, but then the question is, are these enough for w to be a valid adjustment set instead of x? So for that, let's go back to the blackboard. Let's recall the adjustment condition. Y sub t is independent from t given x. This is the adjustment condition I have, and that's true in this graph. Right? Why is that sufficient? So let's try to see the derivation of that. Again, we start from the first principles. You write p of y sub t, and you write this as a joint distribution between three variables, y sub t, x, and t. And then try to get rid of x and t by marginalizing it out. Okay? So t equals t prime, not the same t here, different t, and you get rid of them. This is just a chain rule of probability. Now, if I look at these two, what I did here, I replaced t prime with t. Why can I do that? I can do that because of this independence condition. Yt and t are independent given x. If you condition on x, the value that t takes is irrelevant for distribution of y sub t. So I can replace it like this. And then that means I can push inside t prime summation, because this term does not depend on t prime. So you get this expression, first sum over x, everything, this times sum over t prime. And if you sum over t prime, now you'll see I can just get rid of this t t prime in this joint distribution. So I end up with this formula, just a single summation over x, p of y given xt times p of x equals x. This is vector adjustment. So coming from the ignorability assumption, it's very easy to see why vector adjustment is sufficient with that independence assumption. Okay, but I'm interested in w, not x. So can I do the same thing with w? Question. Yes, there's a question.